Hi, everybody. So yeah, I'll be talking about Arrow database connectivity, ADBC. So of course, the first thing that we need to get out of the way is essentially, why should you care what I have to say? So I work at Voltron Data. My day job now is working on the Apache Arrow libraries straight. That's what I do. I work on the Apache Arrow libraries. I also wrote the first, and I think it's still currently the only book on Apache Arrow itself. So if you're curious, pick up a copy. A lot of info in there, a lot of great information, diagrams, and documentation, links, so on and so forth. But in order to kind of understand what I'm talking about with Arrow database connectivity, we need to first give a quick primer on Apache Arrow itself. So Arrow is itself a high-performance, in-memory, columnar format. Now, of course, that's a lot of buzzwords, but the point is that it is designed to be identical in memory as it is on the wire, no matter what programming language you're working in. The benefit there being that you can pass this data between processes or within the same process without paying any serialization or deserialization cost. It becomes super quick to pass the data around, and works there's implementations for a whole number of languages, C++, Go, Python, Rust, Java, R. There's more than I'm saying, even more than what's listed on the slide. The idea being that if everyone can agree on the same representation, then data can be passed around very quickly, very efficiently, without spending 80% of your CPU time on just deserializing and serializing data every time it goes from one piece of your architecture to the other. Now, if you're not familiar with the term columnar or column-oriented, it's pretty straightforward. Typically, we think of structures and tables in terms of the row-oriented memory buffer you're seeing on the slide. A array of structs, whereas a column-oriented buffer is going to be more like a struct of arrays, where you're grouping everything in the same column together in memory. Now, why would you do this? Because when you're talking about analytical workflows and computational access, you're going to get better I/O, you're going to get lower memory usage, fewer page faults at the CPU level. You can fit things in cache better. For example, on that previous table that we just looked at, if you wanted to compute, get me all the archers in Europe, well, one of those columns, you don't even need it all. Now, if you were in the row-oriented buffer, you have to still read in the data for that column for everything, and then you have to jump in memory across from value to value in memory, probably causing some page faults, and it's just not as quick as being able to just read one chunk of the data, look at the first chunk to get the years, and then process the second chunk of the names. Same thing goes for, vectorization is big in computational right now, like SIMDs, single instruction multiple data. In order to benefit from that, the data has to be in memory contiguously as one chunk, so that you can pass it all to the processor and vectorize computation. When you column orient the data is already in that contiguous chunk that you can then operate on vectorized. So this is Arrow database connectivity. So the first thing we're going to do is talk about, when you're communicating with databases, what is the common workflow? What do you most likely have? And nowadays, most likely you're going to use ODBC or JDBC. And your workflow is going to look something like this. First, your application is going to submit a SQL query to some API, probably JDBC, ODBC. Then you have a backend driver, which is going to translate that query to some database-specific protocol and send it across the wire. The database is going to then execute your query. You're going to get your results set back in the database-specific format. And then the driver is going to take the the result set you got back from the database, translate it to the format that JDBC and ODBC require, and then your application can iterate those results. using a row-based interface, which, as we said, why would you do that if you're doing an analytical workflow and want to get the columnar data? More to the point, if your database does column-oriented computation and you send that data all the way across the wire, if you're using JDBC or ODBC, now you have to convert that into a row-based representation before the application can get it. And it's likely you might just convert it back into a column-oriented representation, which is time wasted, memory used, not optimal. So there's pros and cons, though. JDBC and ODBC are ubiquitous. They're not going anywhere. If you're using JDBC and ODBC, probably to access, say, Postgres or SQL Server or what have you, it's not the easiest thing to switch away from that because that's what a lot of your clients are probably expecting. And so you end up with that conversion I just mentioned, where you're converting those column-oriented native databases into a row-based infrastructure or representation of the data and paying that cost. And then when you want things to go faster, you're going to avoid that cost by instead having to integrate with a specific SDK for that database so that you can then benefit and get the representation you want natively and not pay all those conversions. But now you're going to be dealing with, okay, now I need an SDK for Postgres, I need an SDK for Google BigQuery, I need another SDK for ClickHouse. And so you end up with tons of connectors to do all that adaptation. So that's where ADBC comes in. There you go. ADBC is a single API for getting Apache Arrow native data in and out of databases. Straightforward. Column-oriented, vendor agnostic, as minimal overhead as we can get. The idea is not to completely replace ODBC and JDBC. We're not going to. We know that. The point is that for bulk columnar access, if you are doing analytical workflows and want that large amounts of data in a column-oriented representation, ADBC is where you want to go instead of ODBC or JDBC, which would then cost you having to convert things to row-based. So let's take a look at what that workflow looks like if you're using ADBC. Same workflow. We're going to submit a query using the application. The driver is going to translate that to a database-specific thing, send it across. If you're lucky, and that database is using Arrow Flight for its communication, it becomes straight, really, really easy, and the data can just pass right through when it executes and gets you Arrow data whole way through, no conversion necessary, no serialization, no deserialization, just quick, efficient, fast, column-oriented data. Now, if it's necessary, the driver would also convert it into a native Arrow format. So it allows you to then query row-oriented databases like Postgres, while your application is coded solely against native Arrow record batches that you can then iterate over and operate on efficiently. So ADBC is a specification along with a bunch of things that implement that specification. At its core, ADBC is a header file that defines an interface. The reason for this is because most things can interface with a C interface. And Arrow exposes a C data interface so that you can take that data that came back from the driver and with a zero copy, pass it off to the caller without having to pay any copying costs of the data, you're just passing the pointers around. The intent is for ADBC to be ABI compatible across releases. It uses free functions and enums and other mechanisms in the way it's defined to be as compatible as possible so that things aren't going to break on you. And it's relatively new, so the drivers and the API is still under development, still a lot of work going on with it. But there are currently already C, C++, Python, Go, Java, and Ruby implementations of the interfaces along with several drivers. So in your general ideas, where does ADBC fit? Well, here's a helpful little guide. If your workflow is primarily row-oriented, maybe it's a transaction OLTP, then you're probably going to use JDBC or ODBC. You're probably using a row-based interface. Depends on how you integrate with your vendor, with your database, what you're doing. If you want to do anything Arrow native, you have your protocols, Arrow Flight SQL, BigQuery, storage, gRPC, Arrow protocols. And then you have the actual API you can utilize, ADBC. Now, if you've heard of Arrow Flight and Arrow Flight SQL, you might be wondering why ADBC if Arrow Flight and Flight SQL exist. It's not a replacement, it complements that. When you're talking about any kind of complex database data system, you essentially have, for the most part, three pieces. You have a client, you have a transport, and you have a server. ADBC allows the client side so that you can code against the single client API using Arrow native record batches and data, regardless of what your backend data sources are. And then you can just swap out the driver for a different one, and your application code doesn't have to change. It's the same reason why we use ODBC and JDBC, only we're getting a column-oriented representation natively now. On the server side, if you're a database developer and you build Arrow Flight SQL interface, you don't have to build a driver. Arrow Flight SQL as a protocol already exists as a driver for ADBC. There's even an ODBC and JDBC driver for Arrow Flight SQL. So if you're developing a database and you give it a Flight SQL interface, you've saved yourself a ton of work because you don't need to create a specific driver for your database like you would normally have to do for ODBC or JDBC. So it's a complementary effect here. So let's see what it actually looks like in practice. We'll start with the Python implementation. Recently, we released ADBC version 0.2.0, which included drivers for SQLite, Postgres, and Flight SQL. So the ADBC drivers for Python include a DB API interface so that you can just use DB API 2.0, completely compatible with whatever you're using with Python for DB API things, and benefit from ADBC right away. If you want the data to stay in Arrow format, you can install PyArrow and use fetch Arrow table. And now your data never gets converted into a row-oriented format, and you get the columns of data the whole way through. You can see on the two examples, they're very, very similar. The difference is just which driver you imported and your connection URI. There's also a driver manager. Instead of having to import different drivers, if you want that low level or even higher level interaction or bindings, and maybe you want to have multiple instances that are going to interact with different databases, you can use the driver manager and then create database objects that will use whichever driver you want to use. Remember, that's a specification defined by a C interface. So as long as there exists something it can load that has the ADBC header extern C functions, it can work, period. So that driver manager allows you to use multiple drivers simultaneously without different imports. It allows you to decouple what your stuff is from the different specific drivers. You don't need to have import ADBC SQLite. You can just import the driver manager and parameterize the driver the driver string so that you can load whatever driver you need. It also allows the drivers to become reusable. For example, the Flight SQL driver that Python uses for ADBC Python is actually written in Go, compiled to a shared library, and distributed with the wheels via the extern C functions. And the reason for that is because it allows us to not have to maintain multiple implementations of the Flight SQL driver, and we only have to ship the one shared object library with the wheel with almost no dependencies, rather than having to ship the ADBC implementation and gRPC and ArrowFlight and libArrow. All of it as one almost zero dependency, almost zero, shared object that's shipped with the wheel for Python to use via extern C, and that way, and everything's reusable. Here's an example using Go. The Go implementation contains a wrapper that allows you to use, if you really want to, you can use Go's default database/SQL import and use any ADBC driver, any native Go ADBC driver, or any ADBC driver that meets the interfaces with Go's SQL database interface. It also has, if you're able to use CGO, it has its own driver manager, which then would let you also use any ADBC driver written in anything that exposes the C interface with Go, as long as it just loads the shared object that implements the interfaces. So to kind of drive home the point that this is not something that is terribly difficult to understand, let's look at kind of how the concepts kind of match up. You've got the different concepts here between ADBC against the default database SQL for Go, DB API for Python, the Flight SQL connection if you're using Flight SQL directly, JDBC and ODBC in code if you were writing an application that utilizes these. And you can see that all the things map up pretty straightforward, pretty easy, pretty straightforward. The idea is to be simple, efficient, and effective. Above and beyond just executing queries, ADBC also defines in its interface setups for bulk ingestion. You can stream Arrow record batches into your database as imports. You can handle partitioned result sets if your database happens to allow for different locations to fetch your results from, to benefit from partitioning the result set. ADBC has you covered. It also provides some facilities for transactions so that you're not left out in the cold there. You're not giving up any functionality of your database to use ADBC. It complements your databases. So if you want more information about ADBC or about Arrow, whichever, here's some links for documentation. If you want even more in-depth stuff about Apache Arrow, yes, shameless plug, get my book. Lots of great information in there. There's also a link to a GitHub repo that has all the code samples that are in the book. Examples in the book are also in C++, Python, and Go. So no matter what your language of choice is, you're not left out in the cold with the examples. With that, thank you very much. That's me. I'm on Twitter, LinkedIn,